Okay, so hello and welcome back. So in this video we will talk a little bit about the miscellaneous examples. There is examples 17, 18, 19, 20, and that's it. So 17 through 20. And the examples are check whether or using the following compound statement is exclusive or inclusive. Write the component statements of the compound statement and use them to check whether the compound statement is true or not and justify your answer. So the statement that you have is T, which is you are wet when it rains, or you are in a river. You are wet when it rains. When it rains, or you are wet when it rains, or you are in a river. You are in a river. So now this is a compound statement using or. And you can write the you can write the component statements as, for example, Q, you are wet when it rains. When it rains. And R, for example, you are wet when you are in a river. So of course this statement on its own it's true, and this statement on its own is true, meaning that then the statement T is true, because based on the rule that we had for or, we said that basically either of the statements, if either of the statements is true, then that compound statement is true, or even if both of them are true, then the compound statement is true. But I suppose this is an exclusive or, and it's a little bit messy to it's not always easy to decide whether it's an inclusive or exclusive or, because I do not actually know the exact condition, and no exact condition has been mentioned in this book. Now, the way that I understand it is that if both of them I don't really, I cannot really say anything about this. So let's see what the solution is. It says that or used in the given statements is inclusive because it's possible that it rains and you are in the river. So this is how you decide that. It's because it's possible that it rains and you are in the river, meaning that both of these can happen simultaneously. And well, based on the previous examples that we've had, we kind of used the same kind of reasoning, that if both of these can happen at the same time simultaneously, then it's an inclusive or. Otherwise, it's an exclusive or. So this is an inclusive or. And the component statements of the given statement are you are wet when it rains and you are wet when you are in a river. Here both the component statements are true, and therefore the compound statement is true. Okay, so that is that. In the next question that we have, we want to write the negation of these statements. So for example, you have the statement P, which is for every real number x, for every real number x, x squared is greater than x. The negation of this statement would be if there is at least one real number x such that x squared is less than x, for example, something like that. The negation of p, you can say that it is false that p it means that the negation of p is it is false that p, okay, meaning that it is false that for every real number x squared is greater than x, which means that the condition x squared is greater than x does not hold for all real numbers. This can be expressed as not p, which is there exists a real number x, a real number, or at least one real number x, such that x squared is less than x. That's I know these parts well because I have done this in the previous books. Otherwise, so not p is there is a real number x. There is a real number x such that x squared is less than x. So that is that. There exists a rational number x such that x squared is equal to 2. So the statement is there exists a rational number x such that x squared is equal to 2. Such that x squared is equal to 2, which is actually not true. The only such number would be square root of 2, which is an irrational number as far as I know. But let's see. The negation of q is it is false that there exists a rational number x such that x squared is equal to 2. Thus not q is the statement. So not q would then be there does not exist a rational number x such that x squared is equal to 2. So you can, instead of basically the not q, you can simply say there does not exist, and the rest of it as it is, which can be written as this statement can be written as for all real numbers x squared is not equal to 2. You can say for all real numbers x squared is not equal to 2. X squared is not equal to 2. Oh, I made the same mistake again. Is not equal to 2. Okay. Now the next question is all birds have wings. All birds have wings. All birds have wings. So this is statement R. So the negation of this would be it is false that all birds have wings, and you could write that as basically there is one bird that does not have wings, or there exists a bird which has no wings. There exists a bird which has no wings. Okay, that is not R, or the negation of R. And statement S is all the students study mathematics at the elementary level. All the students study mathematics at the elementary level. So here the negation of S is not S, which is it is false that all the students study mathematics at the elementary level. Or you could say there exists a student who does not study mathematics at the elementary level. So there exists a student who does not study mathematics at the elementary level. So you can say there exists a student who does not study, and so on and so forth. Okay, so question number 19 is using the words necessary and sufficient. Rewrite the statement using the words necessary. These are two important words, necessary and sufficient. Rewrite the statement. The integer n is odd if and only if n squared is odd. So their statement is the integer n. The integer n is odd if and only if n squared is odd. So the integer n is odd if and only if n squared is odd. So what this means is that if I take this part as p, for example, and if I take this part as q, this is p if and only if q. That means that p implies q and q implies p. So if you have P implies Q, that means that Q is a necessary condition for P. In the case of this one, you can say that Q is a necessary condition for P, and also you can say that P is a sufficient. We can say that P is a sufficient condition for Q. So I can say that if you have P then Q, what you can say in this case is that P is a sufficient condition for Q and Q is a necessary condition for P. Meaning that, for example, when we talked about, suppose that, for example, P and Q are two statements that says that, for example, let me take a few minutes break. Okay, so now what this means is that, again, in the case of, basically we said that if a number is a multiple of 9, we said that if a number is a multiple of 9, it is a multiple of 3, for example. Let's take this example as an example. Let's take this statement. So this is an if-then statement. So basically what this means is that if I take this as P and if I take this part as Q, if P then Q, then what that means is that basically when I say if P then Q, that means P implies Q. And again, what that means is that as I mentioned before, we can say that P is a sufficient condition for Q. P is a sufficient condition for Q, and then you can say that Q is a necessary condition for P. So what that means is that when you say P is a sufficient condition for Q, meaning that if P is a sufficient condition for Q, meaning that knowing that the number is a multiple of 9 is sufficient to conclude that basically the number is a multiple of 3. Knowing that the number is a multiple of 9 is sufficient to conclude that the number is a multiple of 3. That is, basically P is a sufficient condition for Q. And when you say that Q is a necessary condition for P, what that means is that basically when a number is a multiple of 9, it is necessarily a multiple of 3. That means that first this part has to be true so that this part can be true, right? So now, coming back to the example that we had, we said that basically we said that this statement over here, then that the integer n is odd if and only if n squared is odd. Now I don't know how they have solved this problem. Let's see. So the necessary and sufficient condition that the integer n be odd is n squared. The odd is n squared, must be odd. Let P and Q denote the statements. The integer n is odd, which is, let's denote this statement by P, and n squared, this is of course all the way up to this point. N squared is odd is, let's take this as Q. Now to check the validity of P if and only if Q, we have to check whether if P then Q and if Q then P is true. So to check the validity of P if and only if Q, we have to check the validity of if P then Q and if Q then P. Both of these have to be checked. So again, what that means is that first you have to check whether this is true, and then check whether this is true, and then you can you can basically conclude that P if and only if Q is true. And so far we have not really discussed necessary and sufficient. Let's see how that goes. So now there seems to be two cases over here. Case 1, if P then Q. If P then Q, we have taken this as case 1. We have taken this as case 1, and case 2, if Q then P, we have taken this as case 2. Now, if P then Q is a statement, if the statement, if the integer n is odd, then n squared is odd, right? When you say if P then Q, that means that if the integer n is odd, then n squared is odd. So if n is if n is an integer and n squared is odd, then basically n is odd. We have to check whether this statement is true, which is basically this one over here. You check this, for example, by contrapositive method. The contrapositive of the given statement is if the contrapositive of this would be basically if not Q, then not P. If not Q, then not P. Then not P. Or you can write not Q implies not P, right? So that means that when you say if not Q, meaning that if n is an integer and n squared is not odd, then n is not odd, something like that. So if n is an integer, is an even integer, when you say if n is an even integer, then n squared is an even integer. So that's basically the statement. So this statement becomes if basically to write it in simple language first, you can say that if basically not Q, then not P. You can say that if n is an integer, and n is and n squared is not odd, meaning that n squared is even, then basically n is not odd, so n is even. Then n is even. Or you can say that if basically if n is an even integer, case 1, I'm sorry. Case 1. I've been. So you can say that if P then Q. No. I gave you some wrong information. I'm sorry. So you have to forget what I said. I'm sorry. I was reading from some other place which was not really related to this part. I was reading from case 2. So I start over. I don't want to edit the video. I start over. So you want to say if not Q, then not P. Meaning and I'm sorry. No, not even this. Not even this. So we want to go for case 1, which is P then Q, and we want to prove that P then Q is true. So if the integer is odd, if the integer n is odd, then n squared is odd. That is the statement. We have to check whether this statement is true. Let us assume that n is odd. So since we want to prove this, then we can assume that n is odd. So assume n is odd. Then n is equal to 2k plus 1. Then you can write n is equal to 2k plus 1 for some integer k. For some integer k. So then n squared is going to be 2k plus 1 whole squared, which is equal to 4k squared plus 1 plus 4k which is equal to 4 times k squared plus k plus 1, which is an odd number. So since this is an odd number, so here we wanted to show that if n is odd, then n squared is odd, which we have proved here. So this is true. Therefore, you can say that n squared is therefore you can say that therefore n squared is 1 more than an even number, hence it's odd. So basically this part is done and it's true. This statement is true. Now let's go back to let's do the basically case 2, which is basically Q then P. And what that means is that if n is an integer and n squared is odd, meaning that if n belongs to the set of integers and n is odd, then if Q then P n squared, if n squared is odd, then n is odd. Then n is odd. So that's what we want to show now. So Q then P means if n is an integer and n squared is odd, then n is odd. So how can we show that? So first we can assume that n squared is odd. Let's see how they have done it. So if Q then P is a statement, if n is an integer and n squared is odd, then n is odd. So we have to check whether this statement is true. We check this by contrapositive method, meaning that the contrapositive of the given statement is the contrapositive of this statement. If you have Q then P, the contrapositive of this statement, is if not P, then not Q, because it's not easy to go with n squared. It's easier to start with the contrapositive, because when you start with contrapositive, then you have to start from not P, and then with not B will end up with n. So since you want to say that if not P then not Q, then not P means that n is even. Not P is basically n is even, based on this statement over here. So then you can say that, of course, if n is an integer and n is even, then n squared is even, something like that, right? So now if you go with this statement, which is n is even, now implies that n is equal to 2k for some integer k. For some integer k. Then n squared is equal to 4k squared, which is an even number. So what we wanted to show was that if n is even, then n squared is even, which basically proves this statement Q then P. So this is also true. And therefore n squared is equal to even. Now the problem is that in the beginning of this question, if I'm not mistaken, well, you can ignore the question. That part of the question you can ignore, because they have not. What they have done is that what they have written is that the necessary and sufficient condition that the integer n be odd is n squared must be odd. Oh, well. Well, the statement that we have here, the integer n is odd if and only if n squared is odd. So now the statement that we have here is the necessary and sufficient condition that the integer n be odd is n squared must be odd. So keep this in mind, and when we move forward, you can make sense of this. Right now you might not be able to make sense of it because it's a basically it's a by condition, okay? But because you have p if and only if q, it's a biconditional, and I explained to you what each part of that actually means. But then when it comes to the biconditional, it becomes the necessary and sufficient condition. The necessary and sufficient condition that n be odd is that n squared must be odd. Okay, so what that means is that it's necessary. It's a necessary condition that it's basically the necessary condition that n be odd is that n squared must be odd. That's a necessary condition, meaning that first this has to be odd, and then this can be odd. And then sufficient is that sufficient means that, for example, going with the example of that number, the sufficient condition that n be odd is that n squared must be odd. Well, for example, if you had p then q, then you would say that basically q, then you would say that q is a sufficient condition for is a necessary condition for q is a necessary condition for p, and p is a sufficient condition for q. Well, I'm not going to talk about this because I might say something wrong. I will simply just not talk about it. Okay, anyway, then the next question is question number 20 is for the given statements identify the necessary and sufficient conditions. So if you drive over 80 kilometers per hour, if you drive over 80 kilometers per hour, then you will get fined. Then you will get a fine, or basically a ticket or something like that. So if you take this as Q, now this is easy to talk about, but the other one was not really easy. And if you take this as P, so what that means is that, so what you have here is if P then Q. If P then Q. And what that means is that What that means is that Q, or you can write it as P implies Q. Now, what you can say about this is that Q is a necessary condition for P. Q is a necessary condition for P, and P is a sufficient condition for Q. And P is a sufficient condition for Q, meaning that knowing that, now going forward with this first, P is a sufficient condition for Q, meaning that knowing that you have driven over 80 kilometers per hour is enough to conclude that you will get the fine. That's sufficient. It's a sufficient condition, meaning that knowing that you've driven over 80 kilometers per hour, that's enough. That's evidence enough, or that's reason enough to conclude that basically you will get the fine. And well, if you want to talk about this in this context, you would say that, for example, when you say that Q is a necessary condition for P, you could probably say that if you drive over 80 kilometers per hour, then you will necessarily get a fine, something like that. Now let's see how they have solved the problem. So the implication, if P then Q, indicates that P is sufficient for Q. P is sufficient for Q, which is what I have written over here. That is, driving over P is sufficient for Q. That means that driving over 80 kilometers per hour is sufficient to get a fine. Okay, so that's easy to understand. Now here the sufficient condition is driving over 80 kilometers per hour. Similarly, if P then Q also indicates that Q is necessary for P. That's what I have written over here. Q is necessary for P. That means that when you drive over 80 kilometers per hour, you will necessarily get a fine. That's exactly what I said. So here the necessary condition is getting a fine, which, well, I mean, logically in human language, it's hard to make sense of it, but in the context of these if-then statements, it does make sense, of course, because it's been defined that way. Otherwise, normal human beings would not be, I mean, you wouldn't be able to use this kind of language in order to talk to a human being. But, well, I suppose this is not talking to a human being. You're using logic in order to decide the validity of some logical statements, which, of course, in that context, of course, it's valid and it does work. So that's that. Now, in the next video, we will talk about miscellaneous exercise on chapter 14. There is like 7 exercises here. We will go through them as well, and then we are done with this chapter. So I'll see you in the next video.